think we will cover amine synthesis on Monday. So that is pushed back a little bit. Let me go ahead and pull up our lab schedule. Oh, where are we? Okay, so yeah, we already talked about this a little bit, but just to kind of remind you, we were originally scheduled to do the amine synthesis here today. We're going to go ahead and push that back to Monday, and that will force the fourth synthesis, that's the synthesis of carboxylic acids and derivatives, back till the Monday after spring break, and then that's going to push your third midterm exam to April 20th. Okay? Yeah. Okay, so does anybody have questions about the schedule? Oh, and by the way, I think I mentioned this also, but just to remind you, whenever you're starting to do the amine synthesis, make sure you're doing amine synthesis 1. Okay, that's the one that we're going to be covering together. There is an amine synthesis 2, and that's going to cover all of this diazonium chemistry that we kind of introduced a little bit on in lab last time, and we will finish off that discussion today in lecture. Okay, so my goal today is to wrap up with amines and then get into carboxylic acids.
Are you going to make assignments on the assignment, like who we present
For
with?
the amine synthesis? Yeah, I'll tell you that in lab.
Okay.
Okay, so like I said, we're going to wrap up with amines today and get into carboxylic acids. That will be the third chapter of Unit 3. Carboxylic acids will go fairly quickly. We possibly could get through that today. But then we move into the acid derivatives, which is a pretty big chapter. So we'll spend a few days there, probably. Okay, so let's go ahead and pick up where we left off. I'm gonna go ahead and record this. All right, so where we left off, we had just finished talking about the Hoffman elimination. And so the only thing that we have left to talk about in the amines chapter is this final reactions with nitrous acid. So this might test your Gen Chem nomenclature skills here for a second. But if you think back to what nitrous acid is, we all know nitric acid is HNO3. It forms from the nitrate ion. The nitrous, any kind of an OUS acid, if you remember, comes from the ITE ion. So this comes from the nitrite ion. And so what nitrous acid looks like is HNO2. Now, what we can do with this is you can take nitrous acid, and if you treat a primary amine with it, we'll go through the mechanism of this in a minute, what it will generate is this diazonium species. However, if you do this with an alkyl amine, it really falls apart rapidly. It's not stable, and it falls apart because it generates nitrogen gas. It's about the best leaving group known to man. And so the nitrogen gas, the nitrogen just kind of leaves, the thing decomposes to give nitrogen and carbocations.
How come when we did our lab, we didn't use nitrous acid? We used sodium
Oh, we'll get there in
nitrite?
a second.
Oh, okay.
So the thing, so basically what I'm saying is that if you're trying to use an alkyl amine, this is not useful. So nobody ever does it with alkyl amines. However, if you do this with an aromatic primary amine, you make an aromatic diazonium, and these are relatively stable, right? You can draw resonance forms where the electrons of the benzene ring get kind of pushed into the nitrogen and help to stabilize it. So granted, you're not going to be able to bottle these and store them for months on end, but you can form them and they will last long enough to where you can do chemistry with them. And that's what we did in lab on Monday, right? So what you're going to see is we can throw a whole variety of nucleophiles at these aromatic diazoniums and end up substituting the benzene ring this way. And this is a really, really useful, versatile way of substituting benzenes. And I will show you in just a minute after we kind of go through the chemistry of this what all you can do with it, but it is a really powerful technique for substituting benzene rings. Not only does it allow you a lot of versatility on what you can put on the benzene ring, but it allows you to do it under remarkably mild conditions. So if you remember, we talked about substituting benzenes before. We had a big chapter on nothing but the substitution of benzene rings. All of those reactions primarily were electrophilic aromatic substitution, and all of those required very, very strong Lewis acids and electrophiles. This will occur under relatively mild conditions. And so it allows us to do a lot of things we were not able to do before, all right? So the question that Danielle had a minute ago is, well, why didn't we use nitrous acid when we did this chemistry in lab? The reason we didn't is because nitrous acid is not stable. So you can't go and buy a bottle of nitrous acid, right? So if you want to use nitrous acid, you have to make it in situ. And the way you typically do that is through the combination of a nitrite salt so in lieu of buying a bottle of nitrous acid, what we do instead is you take a nitrite salt, something like sodium nitrite, and you treat it under acidic conditions. And that's going to end up generating the nitrous acid. So that's not really the active ingredient, if you will, because under acidic conditions, nitrous acid eliminates water, and that's what's going to generate your electrophile, the active ingredient here. So the reaction we're looking at, so that's what nitrous acid would look like. Under the acidic conditions of the reaction, this oxygen will protonate, and that makes a good leaving group. And then in the next step, we just eliminate the water. And that is our active electrophile. This is what is going to ultimately react with the aromatic primary amine, and this is what we call the nitrosonium ion. So what I want to do now is go through the mechanism of this. How is it that we go from an aromatic primary amine to this aromatic diazonium species. So what we typically do is you kind of think back to what you did in lab on Monday. You mixed your aromatic primary amine, you ultimately combined it with that nitrite HCl mixture that you had in the test tube. And then that generated your aromatic diazonium, to which you added the coupling agent. So what's happening in that process is as you add that nitrite HCl mixture to the amine, the aromatic amine is going to go and attack the electrophile. So we end up with something like that initially. And I'm just going to do a minus H plus step to get things back to neutral. Okay, so if you look at where we are currently and where we need to get, right, this is where we are, and this is where we need to get. So what you should notice here from a mechanistic perspective is we have to lose this oxygen. Well, in a mechanistic sense, how do we always lose oxygen? Yeah, we protonate it. Yeah, we have to protonate it twice because we have to lose it as water, right? Oxygen's not going to leave as certainly as an O2 minus. It's not going to leave as an OH minus. It always leaves as water. So that's what we're going to do in the next few steps of the mechanism, is we're going to ultimately protonate it 2 times, make it H2O plus, and then we're going to lose it as water.
Sorry to disturb you. Did anyone lost his car keys on that 2018?
Oh, that's probably me. Yeah, that's probably me.
It's yours, Wanda.
Thank you.
Yeah.
So, that is what we're gonna do. So I'm gonna take one of the oxygen lone pairs. Remember, we're in acidic conditions, so it's not unreasonable to think about going ahead and doing this. All right, and from there, I'm just gonna shift the electrons around a little bit. I'm gonna push the electrons from the nitrogen, the amine nitrogen, in, and that's gonna give the oxygen its lone pair back. All right, and now I need to do another deprotonation step to get nitrogen neutral again. So we're just doing a bunch of proton transfers through this part of the mechanism. And then, as we talked about a minute ago, if I want to make the oxygen leave, I have to protonate it one more time. Okay, so now I have my leaving group, and in the final step of the mechanism, we're just going to push the electrons in and help it leave. And that gives the water's leaving group, and more importantly, generates that aromatic diazonium species. So this works well when you have an aromatic primary amine. So what I'd like to do now is show you why you can't do this with an aromatic, say, secondary amine. Okay? Because this reaction, this process of what happens when you do this with aromatic secondary amines actually has some kind of real world implications. So let's, instead of dealing with aniline, let's deal with this one.
Professor, for
Uh-huh.
the previous example,
Yeah?
is the hydrogen that the OH is accepting, right, is it the same hydrogen that's leaving the end? Or is it?
It kind of doesn't really matter, because it's just going to be a proton from solution. You're in acidic conditions, so you have all sorts of protons around. So in a sense, it doesn't really matter because there's such a large excess of protons. Okay, so this mechanism is going to begin exactly the same way the previous one did, where you have your amine. Under the conditions of the reaction, you will have that nitrosonium, and the nitrogen will go out to attack. So just following the exact same steps that we did previously. We want to lose the proton to get things back to neutral. And then we can think about, again, doing the exact same thing that we did before. We're going to try to start making our leaving group. Shift the electrons in, giving oxygen its lone pair back. Okay, so here's where things start to go awry for us. Because you'll notice I have that positive charge on the nitrogen that I can't give its lone pair back to. If you think about what we did in the previous mechanism, basically right here, all we did was we deprotonated the nitrogen to give it its lone pair back, to get it back to neutrality here. We don't have a second hydrogen on nitrogen to do that in the case of the secondary amines. So right here, there's no hydrogen available to just simply deprotonate to get nitrogen neutral again, which is going to be a problem. You know, you might not see it right now, but let's just keep going. And I think you'll begin to see why this is not gonna go anywhere useful. So you might say, okay, well, who cares? You can't get nitrogen neutral again, let's press on. All right, well, we would need to protonate. Still trying to make the oxygen a good leaving group. Strange. All right, but maybe we can keep going. You know, we've got a good leaving group, so let's just make it leave. we enjoying this mechanism so far? Have you ever seen something like this? Where we have a positively charged atom directly adjacent to another positively charged atom? No, that's never going to form. So the bottom line is none of this happens. The whole thing stalls out right there. That is what you actually make. And this is what's called a N-nitrosamine. And it turns out that they are fairly carcinogenic. And the reason why I bring this up, I said it had some real world implications, is because back about, I don't know, 5 years ago or so, the World Health Organization came out and said that the world needed to stop consuming so much cured meat. So cured meat, these are, well, lots of tasty things to enjoy. Ham, pepperoni, salami, bacon,
Could you slide it up a little bit?
you know, all of that,
sorry.
all of that good stuff. And the reason why they said people needed to stop consuming it is because it's been associated with much higher incidence of various types of cancers, especially like stomach cancers, intestinal cancers, things like that. And the going theory is that if you look at any package, go home if you have it at home, and turn over a package of ham or bacon or something like that, and what you'll see is it'll say contains nitrites, because typically in the curing process they use sodium nitrite to help preserve it. And so if you think about that, all right, so you're eating this stuff that has nitrite in it, where is it going? It goes to your stomach. And what do you have in your stomach?
Acid.
Hydrochloric acid. And so you're creating the perfect conditions with nitrite and HCl to generate these nitrosonium species. Right? That's what we're doing in this chemistry. And so if you have nitrosonium, as we just discussed, in the presence of secondary amines, you're going to generate these nitrosamines. Well, you just happen to have a whole bunch of secondary amines in your body. Proteins, nucleic acids, a bunch of them. And so the thought is through the consumption of these nitrite-containing foods, you generate those reactive nitrosonium, and in the body they react to form those carcinogenic nitrosamine compounds. And so that's why they have come out and recommended to reduce your intake of cured meat products. Now that said, have I stopped eating cured meat products? No. But you know, it's something to think about, I guess. Everything in moderation, right? But in any case, the bottom line is for useful synthetic chemistry, you're only going to use this with aromatic primary amines. All right? So let's see what we can do with these once you make the diazone. Alright, so I think what I'm going to do is just give you a table. And so I'm going to give you a table that has two columns, one that has the X group, so whatever it is you can substitute the ring with, and then I'll give you reagents, which is what you'll use in order to put the X group on. So,
Did you say this is a summary?
Did I say it's a loop?
Did you say this was a summary?
Yeah, it's just all the different things that you can do with the dye, once you make the dye zone. So we can add, a list of halogens. So, the copper bromide salt and hydrobromic acid would add Br to the ring. You can do the same thing with chlorine. Allow you to chlorinate the ring. Group these guys together. They're a little bit different from each other, but you'll see the reason why. But you can do the same thing with copper cyanide and hydrocyanic acid. That'll put a nitrile on the ring. The reason I group these three together is because they are all reactions involving copper salts. And these collectively are known as Sand-Meyer reactions. But continuing down the list, I can put the iodide on the ring simply through the use of sodium iodide. What else can we do? Oh, this one is a really important one. I can make phenols. We talked about making phenols earlier, back when we were doing electrophilic aromatic substitution. If you recall, the way we did that prior was we had to first sulfonate the ring. You know, doing that fuming sulfuric acid, put the SO3H group on the ring, and then we had to follow it up with the molten fusion, right? Liquid sodium hydroxide at 300 degrees. So I told you at the time, that is not exactly kind and gentle conditions. There's a whole lot of functionality that 300 degree sodium hydroxide is just gonna wreck. This is a new, much better way of doing that chemistry. You can make a phenol, and all you really need is dilute acid. So this is a much, much better way of making phenolic compounds. The other thing we can do, we can substitute with an H. Seems a little weird. You know, presumably, in order to do this chemistry, you have to have an aromatic amine. So if you're just trying to put an H there, why would you have ever made the aromatic amine to begin with? But I'll show you a reason why you might want to do this in just a second. This uses a very odd acid. So if you think phosphoric acid would be H3PO4, this uses H3PO2. That's really going to test your Gen Chem nomenclature skills. What is this one? Well, phosphorus would come from phosphite, which would be PO3 or PO3 3 minus. Yeah, I know, that's getting really obscure. It's, I think, and you can correct me if I'm wrong, but I think it's the hypophosphorus acid. But that's testing my memory too, so I might be wrong on that. You can check if you want, but I think it's the hypophosphorus if I'm remembering that right. Okay, anyway, it's a weird one. We'll come back to that in a minute. The other thing that you can do with this chemistry is you could put a fluorine on the benzene. And that is really difficult to do by other means. But it's important to do. Fluorines are very interesting substituents. A lot of drugs have fluorines on rings. A lot of everyday kind of products, pesticides, agricultural products. Fluorine, it turns out, has rather unique properties, and it gives molecules relatively unique properties. And so it's an important reaction to be able to do. The way we do this is using another kind of strange acid, which is called fluoroboric acid. You do have to be a little bit careful, because when you do this, you end up precipitating a diazonium fluoroborate salt that you typically have to filter off, and then you have to heat the solid to decompose the fluoroborate salt to generate the fluorinated benzene. Trick is that that diazonium fluoroborate salt is rather explosive. So you do have to be a little bit careful as you're trying to decompose the salt so it doesn't blow up in your face. But it can be done. And this is a named reaction. We call that the Schumann reaction. So, some of this you may be looking at is like, okay, well, I could already do a lot of that, which is true. You know, I mean, we talked already back a couple months ago. We could put bromines on the benzene, we could put chlorines on the benzene, we could put iodines on the benzene. So what's so new about this? Well, it will allow you to do some things that you were not previously able to do. So for instance, what if I were to ask you, make this. It's pretty simple. You know already how to put a chlorine on a benzene. You know how to put a bromine on a benzene. So do we really need this new chemistry? So let's think about that together. It doesn't really matter which one you start with. I'll start with bromine because I can reach it. If we start trying to put the bromine on the ring, we can do that with Br2, iron 3 bromide, for instance. That would put bromine on. So could I just take that bromobenzene and do a direct chlorination using the Cl2 and FeCl3?
No,
Why not?
because it's gonna direct it either ortho or para.
Yeah, exactly. That's the problem. Remember, halogens are ortho-para directors, yet I'm trying to get these two meta to each other. So yes, I can make bromochlorobenzene, no problem, but it's not going to be meta. So that's where this diazonium chemistry can become useful and allow us to do things that we had not been able to do prior. So, for instance, if I wanted to do this reaction, probably what I would do by the way, anytime you're trying to do the diazonium chemistry, the first step is to put a nitro group on the ring. Because obviously the diazonium chemistry requires an amine, and that's the best way of getting an amine on the benzene is nitrate it, reduce it. Okay? So I'm going to first nitrate. Well, the nitro group is a strong deactivator and thus a meta director. So at this point, I could go ahead and add the halogen. It doesn't really matter which one you add first. Because that's going to put the nitrogen group and the incoming bromine in the right orientation, right? It's going to put them meta to each other. now all I have to do is worry about converting that nitro group into the chlorine. Well, I can't do that directly, but I can reduce the nitro that makes the aromatic primary amine, on which you can do diazonium chemistry. So now all I would have to do is use those conditions that we talked about a minute ago. If you want to use diazonium chemistry to put a chlorine on the ring, all you need to do is make the diazonium and then treat it with copper chloride and HCl. So the way we'll do that is I'll do a step 1, where I treat the aromatic primary halide with HCl and sodium nitrite. So that makes the diazonium. And then a step 2.
Do we need to say HCl, Na, NO2, or can we do just write the HNO2?
I would prefer you to do the NaNO2 and HCl.
Okay.
But then you just do a step 2, and whatever conditions you want to put whatever it is you're trying to substitute the ring with. In this case, the CuCl HCl. All right. Any questions on how we did this or why we did this? All right, then I do want to come back to the hypophosphorus acid one, because it does seem a little curious why we would need a method to just put an H on a benzene ring. So let's look at an example. What if I'd asked you to make that? Well, it'd be easy enough to put a bromine on. Again, just Br2 FeBr3. You see the problem though? Here again, we have a regiochemical problem. Because once you put the first bromine on, it's going to direct any other bromine to an orthopara position. And all of these guys are meta relative to each other. So doing kind of the traditional EAS mechanism is not going to work. All right, well, let's think about another approach. If we want to use diazonium chemistry, we always have to put on the nitro group and then reduce it to the aromatic primary amine. So let's see if that would get us anywhere. Okay, well, doing direct diazonium chemistry here to put on the bromine is still not going to be very useful to me, because I would still end up with a bromobenzene, which is going to direct the other bromines orthometa to itself. But imagine for a minute what would happen if we did just the regular EAS bromination? BR2, FeBr3 on this. Now, for the record, we would probably need to protect this nitrogen because it would interact with our Lewis acid, but we're going to ignore that for the time being. But let's say we actually used an excess of bromine. Remember, the NH2, the amine group, is one of the strongest activators. So if we used excess bromine, where are we going to get bromines? Yeah, depending on how much bromine you use, if you used a large excess, you could theoretically get bromines in both orthos and para position. Well, that is starting to look a lot like my product. The only thing I need to do is get rid of that pesky amine group. And that's what that one diazonium reaction will allow us to do. I can treat this with the nitrite and HCl to make the diazonium. Treat that with the hypophosphorus acid, and it will substitute the amine with an H.
Would it work to put NO2s in excess so that you had all three of those on there, and then reduce them all to NH2s, and then do a substitution of bromine in excess, the CBr and HBr? Would that work too, or no?
It would be difficult, just because trying to get 3 nitro groups on the benzene, it's going to be hard to do, just
Okay.
because each subsequent nitration is going to be slower, right? Because the nitro is a very, very strong deactivating group.
Okay.
And so, I mean, you could, theoretically it would work. It would be hard to do.
In practical
Yeah.
sense.
But this would be a much better way of doing it. I mean, you can get 3 nitro groups on the benzene. I mean, that's what TNT is, right? Trinitrotoluene. So it's possible. It's just difficult to do because those nitration, each subsequent nitration is a lot harder than the first.
Sounds dangerous.
Yeah, could be.
Sounds fun.
Yeah. Okay, any questions about the diazonium chemistry? All right, well, that takes us to the end of amines. So I think we'll just move into carboxylic acids here. I think we'll go ahead and just start with nomenclature. So the nomenclature of carboxylic acids is actually really easy. And the reason I say that is because it really takes a lot of the guesswork out of nomenclature for a couple of reasons. number one, the carboxylic acid is the highest priority group. So it's always gonna win. Anytime you see a carboxylic acid, you're always gonna name the compound as a carboxylic acid. You don't have to worry about some other group having priority because nothing has priority over the carboxylic acid. The second reason, because of that, you never have to guess where to start numbering the parent. You're always gonna start numbering at the carboxyl group. All right, so I'll start numbering there. And then you just follow the normal rules of nomenclature, right? You start assembling your substituents alphabetically. So in this case, we would have, ethyl would go first. And then the hydroxy. And then the methyl. And that's an 8 chain. So if it were just regular alkane, we just call it octane. To indicate it's a carboxylic acid, the suffix that we're gonna use is oic acid. So this would become octanoic acid. All right. We'll look at maybe 2 more. Okay, I can see we have a carboxylic acid here, so I know we're gonna name it as a carboxylic acid. I know also that I'm gonna start numbering at the carboxyl group. All right, and then just start assembling the substituents alphabetically. In this case, the amine would go first. This is a 9-carbon chain, so we'll call that known 6E. And this would, because of the alkene, would become an enoic acid. Any questions on these nomenclature? Okay, the last one I want to show you is what happens if the carboxylic acid happens to be on a ring. So what if you had something like this? Now, be careful, because a lot of times people will look at that and say, oh, it's benzoic acid. But it can't be benzoic acid, right? Because it's not on a benzene, it's on just a regular cycloalkane. So to handle this, we're gonna number the ring starting at the carbon that has the carboxyl group on it. So this is gonna be my 1 position. And then you just follow the normal rules of rings. We can number clockwise or counterclockwise. In this case, you're better off numbering clockwise, so the substituents have the lowest possible number. And so I'm gonna name the substituents first. So we call it a 2,3 dimethyl. Yeah.
After we do this, can we do a what if?
Mm-hmm.
Okay, thanks.
And then to indicate that the carboxyl group is on the ring, we're gonna wrap it up with a mouthful and call it cyclohexane carboxylic acid. And obviously, that root in there can change depending on what size ring you were dealing with, right? You could have a cyclopentane carboxylic acid, a cyclobutane carboxylic acid, whatever it is. All right. What was your what if, Danny?
Well, I wanted to know if there's a place we could put the double bond where it would force the counting to go the other direction,
Mhm.
but it wouldn't be at the 2 position. Like maybe if the double bond was at the 3 position, let's see, 1, 2, 3. If we put it there, and then it was 1, 2, 3, and it would be 4 the other direction.
Yeah.
1, 2, 3. Yeah, put it at the 3, going the other direction. Yeah.
Yeah, in that case, we would number it 1, 2, 3, 4, 5, and 6.
Because the double bond is part of the
It's part of the
parent name.
yeah,
Okay.
because it's appearing kind of in the suffix, you know? So that's the distinction.
All right, thank you.
Okay, any other question? Oh, yeah.
So we don't have to assign a number to the carbon on the carboxylic acid like we do for ketones?
No, never.
Okay.
Because that would be redundant. Because the carboxyl group is always at the end of a chain, and because the carboxylic acid is always the highest priority functional group, it's assumed that you're gonna start numbering at the 1 position.
Okay.
Okay, any other questions on these? On the nomenclature. Okay, I'm gonna switch over to my slides for just a second because I wanna illustrate a point for you. So we just went through and talked about how you handle the IUPAC naming of carboxylic acids. You should be aware that there are several of these carboxylic acids that almost never go by their IUPAC name. So, and the most apparent of which would be the 2-carbon carboxylic acid, right? If you think about the 2-carbon carboxylic acid, IUPAC would call that ethanoic acid. Nobody in their right mind ever calls it ethanoic acid. It's silly. Everybody calls it acetic acid because that's what it's been called for 1,000 years. Another one would be the 1-carbon. Nobody ever calls that methanoic acid because again, it's just been known for so long as formic acid. And that's just what everybody calls them. Those are kind of the 2, I guess, most common ones. I do want to show you, well, first of all, this kind of gets into a different topic, but in terms of their properties, you'll notice carboxylic acids don't particularly smell very good. You know, you've got your rancid butter, your foot odor, your goat odor. I don't know what that is, but it doesn't sound like it smells very good. But they tend to have like sour and kind of acrid smells to them. You know, think like vinegar, right? Vinegar has that, I mean, especially if you're dealing with a strong solution of acetic acid, you know, that can really just kind of make you wince if you get a big snoopful of it. But yeah, they don't particularly smell very good. But the ones that I want to look at with you right now are the ones highlighted in pink. Because you don't need to know these for this class, but most of you will probably at some point be going on to taking biochemistry, and you will need to learn them then, because they are really important in metabolism. So, but again, you don't need to know this from this class, but I'll just give you a little nugget, a little stupid mnemonic device that maybe you'll carry with you into biochem, and to where you'll never have to worry about remembering this at all. And that mnemonic device for caprochloric, myristic, palmitic, and stearic acids is chemists love to make people suffer. So, again, you don't need to know it for this class, but you might find it useful when you take biochem. Okay. The other one, so sometimes people will ask about what happens if you have two carboxylic acids. So for instance, what if you had something like that? IUPAC would call that ethane dioic acid. But for the smaller of these diacids, nobody ever uses the IUPAC either. Instead, you would call this oxalic acid. And it goes kind of, there's a whole series of them, you know, that would be the 2-carbon, the 3-carbon is malonic acid. Succinic acid, glutaric acid.
Do you want us to memorize these?
No. Again, you'll need to learn these for biochem because they're also pretty important for a lot of the metabolic cycles, but you don't need to know it for this class. But I will give you another stupid mnemonic device for this. So that's just going in order 2, 3, 4, 5, 6, and 7. But if you remember, oh my, such good apple pie, that might help you to remember these guys. I know it's real stupid and silly, but sometimes that just does the trick. So, all right, so let's go ahead and look at carboxylic acid in terms of their physical properties. So if you're looking at a carboxylic acid, can these hydrogen bond with each other? Yeah, because you have a hydrogen directly attached to an oxygen. And anytime you have that, you will have hydrogen bonding. In fact, these undergo rather unique hydrogen bonding. They end up doing this type of thing, where the OH of one is shared with the carbonyl of another, and then the other one reciprocates. All right, this is what we call a dimer. So these carboxylic acids are not held together by a hydrogen bond, they're actually held together by 2 hydrogen bonds. And as a result, the boiling points of these things are incredibly high. So just to give you an idea, let me give you, well, let's look at a 3-carbon aldehyde, a 3-carbon alcohol. And I'm just going to give you a 2-carbon carboxylic acid because that'll keep the molecular weights about the same. So if you compare the boiling points of these, remember, an aldehyde only has dipole-dipole and London forces. It cannot hydrogen bond. And as a result of these 3, not surprisingly, it would have the lowest of the boiling points. So it's around 49. Now the alcohol, as we know, that can hydrogen bond. It has a hydrogen directly on the oxygen, and that's going to that's going to increase the boiling point significantly. Right? It practically doubles the boiling point up at around 97. And then you go to the carboxylic acids, so they can hydrogen bond as well, but because of that strange dimerization that they undergo, they're held together by 2 hydrogen bonds, not 1, the boiling point is even higher at close to 120. So carboxylic acids among the functional groups have some of the highest boiling points if you're kind of comparing apples and apples.
Is the carboxylic acid supposed to have 3 carbons?
No, I wanted to give you, the reason why I kind of broke with the series here is because I wanted to keep all of these at roughly the same molecular weight. So because you have an additional oxygen with the carboxylic acid, that's why I kind of shortened the chain relative to the other. Yeah, yeah. Okay, but you actually already knew this about carboxylic acids, about the strength of the hydrogen bond, whether you realize it or not. All you have to do is think about infrared spectroscopy. So we all know that hydrogen bonding causes the broadening of those absorptions. Think about alcohols, think about amines, and think about carboxylic acids. So I've got two IR spectra here. So notice this one down here at the bottom, this is propanol. And you can see it looks like a typical alcohol, where you got that kind of strong, broad absorption at about 3,300 wave number. Now compare that to up here, your carboxylic acid. Notice what is happening to the OH absorption. So it's pretty strong and broad for an alcohol. But the carboxylic acid, I mean, it's like 1,000 wave numbers. I mean, it almost looks like the instrument is broken. But that goes to show you the strength of those hydrogen bonds in carboxylic acids. They're much, much stronger than for alcohols. All right. Any questions on this? All right, then let's go ahead. I'm going to switch back to our notes here. So one of the other features about carboxylic acids, as you probably are well aware of by this point, is, well, they're acidic. So, I'm just going to draw for a minute the ionization expression here. So if you take and you put a carboxylic acid in water, to a certain extent, it will ionize and generate hydronium, which is why carboxylic acids are acidic, right? Anything that generates hydronium in solution is going to be acidic. So my question then is, why are these guys relatively acidic? You know, pKa of something like 4.8, where I can draw a very similar looking ionization equation for an alcohol. Well, looks pretty darn similar, yet the pKa is vastly different. A carboxylic acid is much, much more acidic than an alcohol, yet the ionization expression looks pretty much the same. What's the difference?
Carboxylic acid could give away the proton.
But why does that happen so much more readily than with the alcohol?
It has a resonance structure that'll stabilize
Yeah.
that negative charge.
It has to do with the stability of the conjugate. This conjugate is much more stable than this conjugate. And that has to do with the delocalization, right? I mean, I can draw an equivalent resonance form for that carboxylate. So really, that negative charge is not on one oxygen or the other, right? It's actually spread through that 3-atom grouping, through the carboxyl group. And as we've talked about since the first day of this class, to the extent that you can delocalize or spread out electron density, you're going to be much better off and more stable for it. The alkoxide, there is no delocalization. All of that electron density is squarely on oxygen, which makes it much less stable than this highly delocalized system. So there are some other things we can do that affect the pKa of carboxylic acids. So normally, when we think of carboxylic acids, these guys typically have a pKa in the upper fours. So this one, for instance, is about 4.82. But if you start putting electronegative atoms close to the carboxyl group, you can enhance the acidity. So consider this one. So now I have a chlorine. Chlorine's an electronegative atom. So meaning that it is pulling electron density towards itself. Well, that makes that alpha carbon quite electropositive, which means this alpha carbon is really looking for electron density. So it's going to be pulling electron density out of the carboxyl group. And so it just, this electronegative atom in close proximity just helps to stabilize that carboxylate through induction. So there's an inductive effect by having that electronegative atom so close to the carboxyl group. And this affects the acidity. This guy has a pKa of about 2.8, simply by putting the chlorine close. Now, you have to remember that inductive effects fall off rapidly with bond length. So it's not like if you put the chlorine, 7 carbons down the chain, that it's still going to have a big effect on the acidity. In fact, once you get more than a couple carbons away, the effect is pretty much negated. So once we move it down to the end of the chain, we're pretty much back to where we started from. We're pretty close anyway. But I do want to show you these halogens in close proximity can have pretty dramatic effects. One of the more common organic acids that you'll encounter, especially if you do any kind of HPLC, liquid chromatography type work, is one that's called trifluoroacetic acid, or TFA. And it just looks like acetic acid, except instead of having a methyl group next to the carboxyl, it has a trifluoromethyl group. So now we're not talking about one electronegative atom in close proximity. We're talking about 3 of the most electronegative atoms in close proximity. And so that has a very large stabilizing effect and really affects the pKa value, where this thing has a pKa of 0.23, which is really quite remarkable because that's starting to get down into the level of those strong mineral acids from inorganic chemistry, which is pretty unheard of for a organic acid. Okay, so I want to go through and do a similar exercise with the acids that we did with the amines. And that is, I'm going to give you a series of carboxylic acids and a series of pKa values and see if you can match them up. All right, so the pKa values are all right, so take just a minute and see if you can match these guys up. All right, so what to notice about these is they are all similar benzoic acid compounds. The only thing that differentiates one from the next is the substituent group. So before we jump into this, what kind of substituent group do you think would be good for acidity? What kind of substituent is going to make these carboxylic acid compounds more acidic? Is it going to be a withdrawing or a donating group?
Withdrawing.
Yeah, a withdrawing group. A withdrawing group is going to help stabilize the negatively charged carboxylate. All right, so that's good. So, I guess, which of these groups then are electron withdrawing groups is the next question.
The aldehyde.
Yeah, the only one on here is the aldehyde. That's the only electron withdrawing group of these that we've got listed. So, by that logic, it would make sense that our 3.75 would be here. This is going to be our most acidic compound. So this one is just kind of going to be in the middle because both the hydroxyl and the methyl groups, those are both electron donor groups. This one is just kind of, it's got nothing. It's nothing good or bad about it. It's just there. All right, so because you've got the withdrawing group and these guys are donor groups, I guess having nothing would be better than having a donor group. So I would probably put this one at our 4.2. So that would be the next most acidic. What's the stronger electron donor group between the methyl and the hydroxy? Yeah, the OH. That's a much stronger donor group. So that's going to be the most destabilizing to our carboxylate. So that's going to be our least acidic at 4.55, which makes this the 4.36. Okay. Does anybody have questions on how we made those assignments? Okay. We've got a couple minutes left, so we can go ahead and get into the synthesis of carboxylic acids. We'll just do a couple of these. I think you know most of these, by the way. The most common and easiest way of making carboxylic acids is one that a reaction you've been working with for quite some while now, and that is simply the oxidation of a primary alcohol. Right? So simply take a primary alcohol, and you can use a whole host of different oxidizing agents. KMNO4, the dichromate reagents, Jones reagent, bleach, a whole bunch of different things will do it. To make the carboxylic acid. Alright, another reaction that you're familiar with is the oxidative cleavage of alkenes. Alright, so if I have an alkene like this, we'll treat it with permanganate and heat. Remember what this does is it just takes the carbon-carbon double bond and replaces it with a carbon-oxygen double bond. So the left-hand half of the molecule would give me a ketone, but the right-hand half would give you the carboxylic acid. This one is a little bit limited. But we talked about this whenever we were looking at the benzene chemistry. We can take an alkyl benzene treat it with permanganate. And remember, this is always going to generate the same thing. It's always going to generate benzoic acid. And there was that caveat to be aware of, that you can only do this if you have at least one benzylic hydrogen. So for instance, if you had T-butylbenzene, you could not do this reaction because there would be no benzylic H. And I think that's about all we have time for, so we'll pick up here on Monday, and we will look at the remaining 2 methods of carboxylic acid synthesis, and then we'll do reactions, and then we'll jump into the acid derivatives chapter. All right?